Hi, hello. Welcome to section 5 of chapter 7. So in this section, I'm going to discuss topic called hybridization of atomic orbitals. Um, this is, I would say, is the most important topic if somebody is trying to understand the bonding. So for that, it needs certain basics. We just need to refresh our basics. So that's why I'm going to take you to chapter 3, where we discussed about electronic configuration, and I'm going to ask a couple questions to poke you thinking, and so that I can lead you to the discussion in chapter 7. Let's see, that's my plan. So if you go back to chapter 7, where we draw the electronic configurations in orbitals, we said that beryllium has electronic configuration of 1s2, 2s2. So if you discuss about bonding of any element, you only worry about the outer shell electrons. So there are 2 electrons in outer shell. So those 2 electrons should be used for bonding. Okay. And let's say if an element is forming a covalent bond by sharing electrons, the primary rule is that there should be half-filled orbitals so that they can share electrons. But here, currently, what you're looking at is beryllium is having a paired electron, but no half-filled electrons. But you're saying beryllium can form 2 covalent bonds, for example, with an element like chloride. So how it is possible? How beryllium is forming those chlorine bonds? Those are things that we are going to address. And we are saying here boron has 2s2 and 2p1, only one half-filled orbital, but we know that boron can make 3 bonds. Those are the examples that we use. So how it is possible? And here you can see example of carbon where it has 2s2, a lone pair, and 2 single electrons in 2p. But by now we are so confident that carbon can make 4 bonds. So how it is possible carbon making 4 bonds with a lone pair and 2 single electrons? So what causes these things to happen in a way that we have been discussing so far in this chapter? Those are the questions that we are going to answer here. So hybridization is the answer that answers all of these questions. And hybridization is the most fundamental and bedrock foundation of the bonding, because hybridization correctly, exactly, systematically explains or in detail explains how bonding occurs between atoms. Yes, so far we discussed about Lewis theory, we know how to draw atoms, and we discussed about VSEPR theory. We said like lone pair is electron domain, and any bond is an electron domain, like it could be single bond, double bond, or multiple bond, but we don't know what it really means. We're just drawing them, but we don't really know what it really takes for atoms to form bonds, right? We started discussing a little bit in section 4, where we discussed about valence bond theory, where we basically said that the basis for bonding is that when atoms combine to form each other, if their potential energy is lower than their individual atoms' potential energy, they form bond by overlapping their orbitals one over another. Okay, but there is a fundamental flaw in that. It cannot really explain bond angles. For example, in the previous example here, it says the bond angle is about, I don't know if it is a good example. In certain examples, it has, well, here we can discuss. In certain examples, it has a flaw of not able to correctly predict the bond angle between them, because it just uses the orbitals from electronic configuration as it is, which has its fixed rotation. So there comes the issue. So we are going to use a few examples, like maybe 5, 6, 7 examples in this section, and explain how actually atoms bond with another atoms, and how come they all have like same bond lengths, or how come they all have similar character when they form bonds. Let's see if I have any example like that. Just a second, just give me a second. Let's say this is beryllium chloride. Okay, so in this beryllium chloride, it is just electronic configuration, right? it has 2s2, which means, first of all, it is not possible to form bonds. And if it is possible to form bonds, it must be one from s orbital, one from p orbital. In that case, what should happen is technically an s orbital is round and a p orbital is perpendicular. So the bond angle between two chlorines, if it is uses a s orbital and a p orbital, should be perpendicular to each other like this. And bond angle should be like 90 between two chlorine atoms, right? Should be like this, 90 degrees. However, we already know that according to Lewis theory and VSEPR theory, the bond angle between two chlorine atoms around the beryllium is actually 180, but not 90 degrees. It's not using two p orbitals to make a bond, or it's not using one s orbital and one p orbital to make a bond with two chlorines. To have one is perpendicular to another. It is even hard to imagine because it's wrong. It's wrong because two chlorines are completely opposite to each other according to VSEPR theory, and they should have bond angle of 180. That's what we discussed. But when you just look at the fundamentals of electronic configuration, it doesn't quite match. So what it means is you need to explain what is happening to support the VSEPR theory. So VSEPR theory is correct, nothing wrong with the VSEPR theory. But we are saying valence bond theory cannot support the VSEPR theory, which is correct. So we are going to rework on our bonding theory, which is called hybridization of atomic orbitals, to explain and support the Lewis structures and VSEPR theory. So our goal is to explain how BeCl2 actually have the linear geometry and 180 degrees of bond angle using the hybridization of atomic orbitals. Okay, what is hybridization of atomic orbitals is atomic orbitals of atom will undergo mixing of atomic orbitals to form a new hybrid orbital to bond, or just before they bond. Again, it's a cool concept. Let me say it again. So when atom is ready to make a bond with another atom, so atom will mix up its atomic orbitals and create new hybrid orbitals that uses to make bonds with another atom. So it's not going to use its individual atomic orbitals. That's why it follows the VSEPR theory seamlessly. That's why these bond angles are so accurate. That's why these molecular geometries are so accurate. So let's dig into how BeCl2 happen to have the bond angle of 180 but not 90 degrees. Okay, I already discussed some of these there in the previous slide. So we are saying that BeCl2, according to VSEPR theory, has a 2 electron domains, so it should have linear geometry. So let's prove that. So for that, our goal is to show how beryllium atomic orbitals converting into hybrid orbitals, then bonding with the chlorine. Because if you just use the atomic orbitals beryllium, no way you can prove that it is going to have linear geometry and the bond angle of 180. That's why our goal is to learn in this topic, in this section, how individual atomic orbitals are forming a new atomic orbitals called hybrid atomic orbitals. Okay, so let's look into that. So this is what ground state electronic configuration of beryllium. First of all, it has just a lone pair. It's not useful for us to start making hybrid orbitals. So what do? You would excite this beryllium. You would promote the electrons from beryllium lower similar shell, lower subshell of shell 2 to higher subshell of shell 2, because they still belongs to the same shell, right? 2s and 2p belongs to same shell. So because they belong to the same shell, it's not too hard to promote an electron from lower subshells to higher subshell for the greater good of the element. What is the greater good of the element? Beryllium get to have more electrons around its valence shell and maybe more stability as a result. So beryllium atom would willing to promote those electrons by spending some extra energy, because as a result at the end, if it start making bonds, it could gain back that extra stability, it could gain back that energy back. So any element that is in ground state, if it senses that it's going to achieve more bonding, they would undergo promotion, okay, because it got the stability as carrot for the mouse. So electron from the ground state electronic configuration undergo promotion to maximize the bonding. Why any element undergo bond promotion is increase of the bonding is the key. Increase of the bonding is an exciting thing because they can accommodate more electrons. The beryllium element nucleus can experience more electrons in its surroundings. So it will have relatively completed electronic configuration in its orbitals instead of just having 2 electrons only. So it underwent promotion from 2s2 to 2s1 and 2p1. Now, would it just make bonding with 2s1 and 2p1 with the 2 chlorine atoms? If it does, one chlorine BCl chlorine atom should be not same as another chlorine Bl atom, because one beryllium electron is from 2s and one beryllium electron is from 2p, which means the bond made by one chlorine atom should be different from bond made by another chlorine atom. But what we know is both of the chlorine atoms has the same bond length, same similar bonds. There is no difference between them. So which means beryllium is not actually bonding with chlorine using its 2s1 and 2p1 electronic orbitals. How do we know? Because when you check the bond length of beryllium chloride in beryllium chloride molecules, it is found that they both have similar bond length. It wouldn't be possible to have similar bond length if the bonding is happening between 2s of beryllium with the 3p of chlorine and 2p of beryllium with 3p of chlorine, which means these individual atomic orbitals are undergoing hybridization before they bond with chlorine atom. That is the only way. So as a result of not having the same bond length between beryllium and chloride, between 2 bonds of beryllium and chloride, we know that those 2s1 and 2p1 atomic orbitals underwent hybridization to form 2 new sp orbitals. That is the coolest thing that I find in chemistry. So atomic orbitals of individual subshells from S and P or D, they always combine and mix and match and reshape the electron cloud between them to form new hybrid atomic orbitals, only to make much more stronger bonds, much more unified bonds, much less fuss in the bonding, because if one is strong, one is shorter, one is longer, there is always an issue. So just before bonding, atom creates its own hybrid orbitals by mixing all of its valence electrons. Again, this is the key, and that I'm going to use it many times in this part and next part. An atom would mix all of its atomic orbitals just before it participates in bonding and creates hybrid orbitals for all of its valence electrons. So currently beryllium has only 2, so that's why it is forming 2 hybrid orbitals, one with 2s, one with 2p. So because it is redundant to say that it is from shell 2, so we just don't see it anymore when it comes to hybrid orbitals. So 2s and 2p atomic orbitals converts into 2 sp orbitals. There are 2 s and p orbitals. So these hybrid orbitals will be used to form bonding with the 2 chlorine atoms. So how these sp orbitals are going to look is, this is how it is going to show. An s orbital shape is spherical, a p orbital shape is dumbbell. So when they both combine, they enlarge into larger a dumbbell shape. Not exactly p, not exactly s, but kind of like larger dumbbell shape. So the new hybrid orbitals is going to look like this. So there are 2 sp orbitals as a result of 1 s and 1 p orbitals hybridizing with each other. This is how they were mixing here to form 2 new hybrid orbitals. And what's the difference of after and before forming is, before it forming, before it forming hybrid orbitals, this is what you will see. There is a single electron in this circular spherical s orbital, and there is another single electron here in the p orbital. But in new form, you have two sp orbitals. This is one sp orbital, and this is another sp orbital. Remember, it looks like this: large and small. You don't see that small part behind. That's why it just looks like one large one, but there are actually two combined sp orbitals there. Now, beryllium is ready to bond, and here you can clearly see that because beryllium has a two sp hybrid orbitals, two electron domains, it is keeping them away from each other in 180 degrees apart. That is how beryllium has two bonds 180 degrees apart. This is the main reason why it has been separated into 180 instead of, like 90 degrees between a s and p orbital like this, which is not happening. This is not observed, but this is observed. This is observed because a s and p orbital of beryllium hybridized to form a two sp orbitals. Okay, so when beryllium is ready to bond with chlorine, it bonds with two chlorine elements, and it uses the 3p orbital of chlorine, and it uses the sp orbital for each to form two bonds. That's why you don't see difference between one chlorine bond to another chlorine bond, because beryllium is using same sp orbital and chlorine is using same 3p orbital. That's why both the beryllium and chlorine bond angles are similar, or same, not even similar. Okay, that's all about hybridization. And everything that I'm going to do from now is repracticing the same thing on boron as an example, on carbon as an example, on nitrogen as an example, on oxygen as an example, or fluorine as an example. So there is a pattern that you can sense, and by problem 2, if not by the end of this problem now, by the end of problem 2 or 3, you would get this topic easily. Okay, so do you guys see that I got excited? This is really exciting stuff for me. So let's work on another example, BF3. So BF3, so let's explain how the bonding occurs. Determine the number and type of hybrid orbitals necessary to rationalize bonding in BF3. So the question is asking, find how many orbitals are necessary to rationalize bonding in BF3. So before we do that, first you always need to draw the Lewis structure of any molecule from the knowledge that we have, and use the valence electron theory, the VSEPR theory, to determine how many hybrid orbitals there should be needed to explain the bonding and bond angle. So Lewis structure of BF3, as we know, if you use the rules that we discussed in chapter 6, it is BF3, one boron in the center with the 3 fluorines around. And according to VSEPR theory, they should be in trigonal planar shape with 120 degrees bond angle apart from each other. So what it means is there are 3 electron domains around the central atom because it is connected to 3 fluorine atoms. So what do we need to rationalize the bonding in BF3 is to come up with the 3 hybrid orbitals for boron. Again, we need to come up with 3 hybrid orbitals from boron side to react with the 2p5 orbital of fluorine of 3 fluorine atoms to explain how actually bonding occurs. This is the most important information in this section for you. Because everything else you already kind of exposed to, but this is the kind of like really, really important information. So when you are ready to explain bonding, so this is how you would come. You would check how many number of electron domains around the central atom. Here your central atom is boron. So then based on those number of electron domains, you would create those many hybrid orbitals, because there is always a chance to create more, but you don't always need to create more. The number of hybrid orbitals required to create is always extracted from the Lewis structure of a molecule. So if Lewis structure of a molecule tells you that you need 3 electron domains, you only create 3 hybrid orbitals. You do not create more than 3. Again, I'm going to repeat this multiple times because this is important. Draw the Lewis structure, and identify how many electron domains around the central atom in the Lewis structure, because that information will tell you how many hybrid orbitals should be around the central atom. So based on that information, you would try to create those many hybrid orbitals only. It doesn't matter if you have more electrons available also in the electron configuration, you don't use them. You only use number of required electron domains equal to the hybrid number of orbitals, because that's what going to explain the bonding, that's what going to explain the molecular geometry. Okay, so now our goal is to create a 3 hybrid orbitals. Let's work with the electronic configuration and do promotion of the electronic configuration if required. So boron has the electronic configuration of 2s2 and 2p1. Obviously, we don't have a 3 atomic orbitals to start with, so you need to create total of 3 atomic orbitals at least. So we did that in the promotion here. Then you are going to create the necessary amount of hybrid orbitals. So how many we need is, we need 3 hybrid orbitals because we have 3 electron domains. So you're going to combine the necessary atomic orbitals, which are 3 of them, to create 3 atomic orbitals. So that's what we did. We put the 1 electron each in 3 atomic orbitals, and we left the empty box alone. If it is empty, if it is full, it doesn't matter. All you need to know is how many atomic orbitals you need to create, so that you will combine those many atomic orbitals to create them. So now here, this is how you would this is how you would title the hybrid orbitals. You would title the hybrid orbitals after how many atomic orbitals you mixed to create new hybrid orbitals. Here, you used a s orbital and 2 p orbitals to create new hybrid orbitals. So your name should reflect that. So you created sp2 orbitals. There are 3 sp2 orbitals. So when somebody reads the number sp2, they understand that, oh, there is a s atomic orbital and 2 p atomic orbitals mixed together to form this sp2 hybrid orbitals. Now, let me show you how it actually look. It's something like we already did. So to create the hybrid orbitals, we used 2s of boron and 2p of boron and another 2p orbital of boron. Remember, boron has, there are 3 subshell, 3 orbitals in p orbital. So there are 2 that we are using. So when you combine 1 s orbital with the 2 single p dumbbell orbitals, you will create 3 sp2 orbitals. They look a little bit larger if you notice any difference from sp to sp2. sp is a little bit smaller, but of the same shape. sp2 is a little bit larger, but of same shape dumbbell. So this is what before boron forms hybrid orbitals with a 2s orbital and 2 2p orbitals and 1 mt orbital. Let me label that. The 2s orbital here, and this is a 2p orbital, and this is another 2p orbital with an electron, but this is 2p orbital but empty. That is empty that I'm trying to write. But after mixing, you have an sp orbital here, another sp orbital here, and another sp orbital here, and an empty orbital here. Empty orbitals can carry, you cannot do anything with them. You cannot eliminate them because they were already there. But there are 3 sp orbitals now ready for bonding, which means you can take it to expose it to the fluorine, where each fluorine uses its empty half-filled last p orbital to form 3 new single bonds with boron. That explains why here boron has the bond angle between each of these bonds as 120, because boron uses 3 sp orbitals that are 3 electron domains separate from each other at 120 degrees angle in trigonal planar shape. That is how boron has this trigonal planar shape with the bond angle of 120. See how amazing is that? Now we know exact reason why these molecular geometries and bond angles exist. Now let's take this enthusiasm work on a couple more examples. CH4. Let's explain the reason behind why CH4 contains all bonds of the same bond length instead of having different bond lengths like bond between S and H, bond between 2s of carbon and a H atom, and bond between 2p orbital and H atom should have different bond lengths, right? But in reality, all of these happen to show that same bond angle. So there must be some reason behind it. So let's dig into it. So how do you do? How do you explain how many types of hybrid orbitals are necessary to rationalize bonding? Is we will start with the Lewis structure of CH4. So CH4 Lewis structure contains carbon with 4 single bonds. Then you would identify how many electron domains are present. That tells you how many hybrid orbitals you need. There are 4 electron domains present. So that tells you that you need 4 hybrid orbitals. So again, this is most important information in doing these steps. Step 2 tells us that you can only create as many as electron domained hybrid orbitals. You can only create hybrid orbitals that are equal to the electron domains present in your Lewis structure. So because you have 4 electron domains, you're going to create 4 hybrid orbitals. That's what it tells you. Now let's go and work on creating 4 hybrid orbitals for carbon. So now here, if you see here, our goal in step 3 and 4 is to identify what is the ground state electron configuration for carbon and do promotion if it is required according to the need for the creating hybrid orbitals. So currently what you see here is only 2 single bonds here for carbon and a lone pair. It's not going to cut it because we need to create a total of 4 hybrid orbitals. So which means you need to excite the electrons to higher subshell of shell 2 so that you will maximize the bonding that is going to be useful for the hybridization of the carbon atomic orbitals, right? So that's why we are doing promotion. Now you have a single electron in each one of the subshell of shell 2, 2s and 2p. So now step 3 is also again important. So here, when we're going to combine the necessary atomic orbitals to generate the required number of hybrid orbitals. So what it means, how many hybrid orbitals you need is 4. How do we know? Because there are 4 electron domains around the carbon. So you need 4, and you look for if you have enough atomic orbitals. We do have enough atomic orbitals in each of these shells because there are 4 of them here, 1 here, 2 here, 3 here, 4 here. Then using those 2s and 2p 4 atomic orbitals, you're going to create 4 hybrid orbitals. So once you create those 4 hybrid orbitals, we are doing step 5 and 6 combinedly. That's why you already put electrons in the sp3. So why I'm calling this one sp3 again? You're going to tell how many atomic orbitals are mixed in the creation of hybrid orbitals. In the creation of carbon hybrid orbitals for bonding, you used 1 s orbital and a 3p orbitals. That's why we labeled it as sp3 hybrid orbital. Okay. Again, I'm going to show you how they mixed. This is kind of repeated information. You should sense the trend by now. So a 2s orbital here, and a 2p orbitals all combined to form 4 sp3 orbitals. So this is 1, 2, 3, and 4. 4 sp orbitals ready to bond. Now, because you have 4 electron domains in the form of sp3 orbitals, carbon distribute them in the bond angle of 109 with the molecular shape of tetrahedral. That is how carbon with 4 bonds has the shape of tetrahedral and bond angle of 109, because it has to separate these electron domains of sp3 into maximum separation to avoid the repulsions between each of the sp3 hybrid orbitals. Again, this is before, which is not useful for us because it does not explain the bonding. It does not explain why all of the bonds in CH4 are equal bond length. This is what actually happened just before bonding. because all of the atomic orbitals are mixed to combine to form new hybrid orbital. So they were ready to bond with the hydrogens. It bonded with the 4 hydrogens of 1s orbital of each hydrogen. That is how it formed the CH4 with a tetrahedral molecular geometry and 109.5 degrees of bond angle. Okay. All right, we discussed a couple of examples, but we're going to discuss a few more. But by now you should see the trend, and if you're comfortable, you can even start doing the same stuff by your own. But I'm going to explain remaining couple of problems as well. So again, the question is asking similar question. Determine the number and type of hybrid orbitals necessary to rationalize bonding in PCl5. So draw the Lewis structure. To draw the Lewis structure, find how many electron domains are there, so that it tells you how many hybrid orbitals you need. So there are 5 electron domains. So you're going to need 5 hybrid orbitals. Remember, phosphorus has only 3 single electrons but a lone pair, so which means we have work to do. So get the electronic configuration of ground state electronic configuration of phosphorus and check if you can maximize the bonding by sharing the unpaired electrons through promotion. So here are all the subshells of shell 3, 3s2, 3p3, but 3d0. Currently, you don't need to use in the ground state. But if you are going to have 5 hybrid orbitals, you cannot just have 3 single half-filled orbitals. You have to have 5 single half-filled orbitals. So how do you do that? By sending a single electron, by sending one single electron to an empty orbital. So you're going to do promotion to do that. Now you have 3s1, 3p3, and 3d1 as your excited state electron configuration. But we know that it's not going to be enough to start bonding because 3s offered electron is different from 3p and it is different from 3d. But it's not the case that we are going to expect in PCl5. We are expecting that all PCl bonds are same bond length, which means they must be using hybrid orbitals of phosphorus to bond. So because we already know how many electron domains are there in PCl5, 5 of them, we are going to work to get 5 hybrid orbitals. So we are going to combine all necessary hybrid orbitals like this to make the new. So we are going to combine all of the atomic orbitals that are necessary to form the bonding to form the new hybrid orbitals. Because here for the phosphorus, you are combining one s and a 3p and another d orbital. The name is going to be sp3d hybrid orbital. So phosphorus is going to use 5 sp3d hybrid orbitals to bond with the 5 different chlorine atoms that are of same bond length, but with the geometry of trigonal bipyramidal. Why trigonal bipyramidal? Because phosphorus now has a 5 sp3d hybrid atomic orbitals. Phosphorus, just before bonding, it has the responsibility to adjust its 5 of the bonds to its maximum possible distance one from another to avoid the repulsions between each of the sp3 hybrid orbitals of its own. So it adjusts 3 of them in the trigonal planar shape and 1 above and 1 below to have the trigonal planar bipyramidal shape. That is how PCl5 has trigonal planar bipyramidal shape. We are just, I guess, leaving you with the kindness of not going over octahedral example as well, but by now we discussed the how sp orbitals form, the linear shape, how sp2 hybrid orbitals form, how sp3 hybrid orbitals form, and how sp3d hybrid orbitals form. So even if I ask you to do that by your own, I'm sure you could do that. You could take an example like SF6 and do it yourself. You should be able to easily come up with octahedral shape by your own if you use the example SF6 for that. Okay? I'm sure you could do it. All right. So let's work on this problem. We're towards the end of this section. So ammonia, as it says, has chemical formula of NH3. It has the trigonal pyramidal molecule geometry. And what we know already, according to molecular geometry, is that it has a bond angle of 109, 107. But how do you explain that? Because it is only using 3 single half-filled atomic orbitals, because the issue with the nitrogen is it already had a lone pair and it has 3 single electrons, and in NH3 it is already using its 3 single electrons. So there is something that you need to pay attention to. I guess I'm too excited here, so I'm going to slow down a little bit when I talk. So the question is asking, how do you explain the bond angle of 107 in NH3 where it is only forming 3 bonds? How do you explain according to hybridization? So our strategy is going to be same. We will start with the Lewis structure. According to the Lewis structure of NH3, nitrogen has the lone pair and 3 single bonds. So what does it mean is, according to the Lewis structure of NH3, with a lone pair on nitrogen, nitrogen has 4 electron domains around it. So it required you to create 4 hybrid orbitals, because that's how we have been doing all along. You would look how many electron domains are present on a central atom, then you would create those many hybrid orbitals, because all the electrons around the central atom has to be from the same hybrid orbitals. So this is the electronic configuration of ground state electronic configuration of nitrogen 2s2 2p3, but it's not currently helping us to correctly predict the bond angles and the molecular geometry. So we are going to discuss about that. Because if you look at the nitrogen electronic configuration here, right there, 2s2 2p3, those 3 hydrogen bonds, if they were from these p orbitals like this, they were perpendicular to each other. So as a result, they should have the bond angle of just 90 degrees, because all 3 p orbitals are perpendicular to each other on x, y, z, e axes. So, but it is not the case. We already know that nitrogen has, NH3 has a bond angle of 107. So we have to come up with a reason to explain why it has 107 as a bond angle, or approximately 109, but not 90 between nitrogen and hydrogen bonds. So going back to the Lewis structure of nitrogen, we already discussed in the previous slide that nitrogen has 4 electron domains around it. So it means you need to create 4 hybrid orbitals. Then maybe you can explain why the bond angle is 107, not 90. So let's do that first. So how do you do that is, this is the first time you're seeing. So it might be a little bit new, but whenever you already have a filled lone pair and you're going to not use them, still use it as it is, you still required to create hybrid orbitals that includes the lone pair. Okay, because you know how central atom is arranging all of these electron domains around it. Central atom only cares about pairs of electrons. That pairs of electrons can form bonds or lone pairs. It doesn't matter to the central atom. That's why for central atom, they were all equal. It could be a lone pair hybrid orbital, or it could be a bonded hybrid orbital. So when you're required to create hybrid orbitals for any central atom that already has lone pair, you must include that lone pair into the hybrid orbitals as well. So you are including this lone pair into hybrid orbitals. That's why you are calling these hybrid orbitals as sp3. What it means is you use 1 s orbital and 3 p orbitals. So you have 4 sp3 hybrid orbitals, but one of them is a lone pair, which means you can only make 3 bonds, which is what the structure of NH3 says. So what is one thing new for you is, in this example, you just learned that When you don't have to do promotion to maximize the bonding, like in the case of nitrogen, where it already has 3 bonds available to bond with 3 nitrogen atoms, you still has to do hybridization, including using the lone pair from the nitrogen atom or any atom. Because for the central atom, all of these paired electrons are same. And central atom only cares about distributing them according to VSEPR theory to minimize the repulsions. So that's why you have for nitrogen in the bonding sp3, 4 sp3 hybrid orbitals with one of them as a lone pair. So nitrogen with its one lone pair and one single electron in each of the other 3 orbitals bonds with the 3 hydrogen atoms by having a lone pair on it and bonding with the hydrogen atoms like this. That is how nitrogen happened to have the bond angle of 107. I want to say 109, but 107, but not 90 degrees. So why 109, but why not why 107, but not 109 to be specific is lone pairs take up more space than they actually should. So actually 4 electron domain should have the bond angle of 109 because of the lone pair of nitrogen, it takes up more space. So it pushes the bonds much more closer by occupying more space. That's why 107. So what did we discuss in this chapter is really, really, really important because it just explains basis for any bonding. So if you are the one that is going to take organic chemistry in future, save these notes and save this video because not many people will explain in this detail. And if you're lucky, if you get one, but I don't see many people really spending time and discussing in detail about how the bonding works. But this is most important and one of my favorite topic in actually understanding how the bonding works. That's why I spend enough time on it. And we use many examples to explain it. I hope you get it for the first time. If not, watch it second time or maybe come to me. I will re-explain again in person. Okay, good luck. I'll see you in next topic of chapter 7. I am so happy to talk about this stuff. Hybridization is exciting.